the fact that it's not just a strong nucleophile, it's a strong base. So any trace of acid will kill your gradient. Any functional groups that contain acidic hydrogens will be a problem. Any functional groups that contain electrophilic molecules in the molecule you're trying to make a gradient is going to be a problem. So this particular problem, we looked at this, which are molecules that are good substrates or poor substrates for a gradient. So for example, this is telling you you've made this gradient and you're gonna put this gradient, let's say, in water. What happens when you put that gradient in water? This is a base, right? Your base attacks an acidic hydrogen, and what you're going to form is basically methane, and then you're going to be left with a hydroxide ion, which presumably is somewhat paired up with this, right? But that's effectively the reaction that kills your gradient in the presence of water. The gradient picks up hydrogen, and it never gets to attack whatever carbonyl or compound you're looking at. Right? So write equations for what happens when the gradient of methyl iodide attacks acetylene, and what happens when it attacks acetone. Write the products of those two. Just sign on top, it's okay. All right, so your gradient, terminal acetylenes have acidic hydrogens, right? We saw that in chapter 9 when you use like sodium amide, you can extract that and get acetylene ion. So this is a strong base, it's certainly going to act as a base here, extract this hydrogen, and then form this, and of course, form methane again. As a CH3 picks up a hydrogen and forms methane, and then your acetylene ion that forms will pair up, in this case, form a salt. Okay, so again, you're killing your gradient with an acidic hydrogen. It cannot act as a nucleophile. It is acting in both of these cases as a base. In this case, yes, it would be acting as a nucleophile, attacking here. Right. And well, unless I put it in water, you're just going to form this for now. Right, then oxide ion, and eventually when we hydrolyze that, then we end up with alcohol. But in this case, this is acting as a nucleophile. You get that? Just highlighting, in this case particularly, that acidic hydrogens are just not a good thing to have a lot of green, and we expect it to act as a nucleophile because instead it's going to act as a base. Okay, so so far, the thrust of this chapter is how do we make alcohols? And initially we reviewed ways of making alcohol and a simple reaction in alcohol that using hydroxide, adding water across a little bomb, a particle and then a particle, all of these things. And then this new using a grid or an organic. Now we're going to look at yet another way of making alcohols, and that is reduction of a carbon. So when in chapter 8, when we had a carbon-carbon double bond, you would add a hydrogen with some catalyst, and the net result is your double bond became a single bond, and you added hydrogen to each of these carbons. It is certainly possible to have a carbon double bond oxygen and do the same, add a hydrogen across the double bond, and the net result is going to be forming a single bond and then adding hydrogen and hydrogen. Okay? In both of these cases, this is called a reduction. We are reducing. Well, reduction has a couple of accepted interpretations, but one of them is to add hydrogen, either hydrogen in the form of H2 or hydrogen in the form of a hydride. So this is a reduction. Now this particular one only works with ketones or aldehydes, not with carboxylic acids, not with esters, but only for ketones and aldehydes. If you wanted to reduce, let's say an ester or an acid chloride, then, or a ketone or an aldehyde, an alternative to that would be to come in with a hydride ion. Because your hydride ion would use these two electrons to adhere. You form this. And then when we add this to, let's say, water H3O plus, then this picks up another hydrogen, and now we have this product. Okay, so whether you're starting from this and using hydrogen to get this alcohol, or you're starting here, you're getting basically the same alcohol. Now, where does hydrogen ion come from? It comes from lithium aluminum hydride, sodium borohydride. So these compounds are compounds that at the center, let's say if you have a boron or an aluminum. These are elements that are in group 3. So they have 3 valence electrons as an atom, which means that to form neutral compounds, they form 3 single covalent bonds. Right? Those would be your neutral compounds for boron and aluminum. Now, if I had a hydrogen ion, we can form a covalent bond by sharing 2 electrons. So if I were to share these 2 electrons, then I would still have a negative charge. So we would have this negative ion that we can then pair up with a positive ion, sodium or lithium. Okay, so that would be sodium borohydride or lithium aluminum hydride. But effectively, these are sources of a hydrogen with 2 electrons and a negative charge. That is the source of your hydrogen ion. Okay. Now, this is milder. This is stronger. So a milder, and this is a reducing agent, right? Causes a reduction of something else, where the reduction is getting a hydrogen. So these are reducing agents. So a milder reducing agent like sodium borohydride will reduce aldehydes or ketones to alcohols. But not your esters or acid chlorides or things like that. Because for that, you need a stronger reducing agent. So your stronger reducing agent, like lithium aluminum hydride, will serve to reduce aldehydes and aldehydes, ketones, but also your carboxylic acids and esters and acid chlorides and whatever, down to the alcohol. Okay, so you just need to be somewhat cognizant of what these things do. And all of them add hydrogen and reduce the carbon double bond oxygen to a carbon single bond oxygen and alcohol. Now, so, if you have the
to the previous page.
Again, I think I've said this a few times, but all of these notes are always on D12, like class problems and notes. So if somehow you don't have time to copy everything, you can always refer to D12 to see all of this. So taking pictures, you can take the class if you want to, but as far as taking pictures, don't worry about it. Now, your hydride ion, these are 2 different reactions, right? In this case, this is an addition across a double bond. In this case, this is a nucleophilic addition of a hydrogen ion to the carbonyl to form this alkoxide ion. And then as a second step, you would need to add H3O plus. So typically what you would write in here is 1, I'm gonna add the sodium borohydride, 2, I quench with acidic water to then give me the alcohol. And without quenching, I just have the alkoxide ion. And the same would be true here, 1 reacts to this, 2 we quench. Now, for an aldehyde or ketone, so let's say I have this iron, and let's say that I come with a hydrogen ion. This could be sodium borohydride or lithium aluminum hydride. I'm going to add once. I'm going to form the alkoxide ion, and then quench this with water, and I'm going to end up with so we're adding 1 hydrogen ion, 1 hydrogen here, the other one's coming from there. If I start, and this would be true for ketones as well. Now, if I start with, let's say, an acid chloride, and I add a hydrogen ion, okay, eventually we're going to do the same thing. We're going to form this alkoxide ion. But now, this alkoxide ion above had nothing it could do. It would just remain like that until I quench it. In this case, this can do something because this is a good reading. So what it can do is bring these electrons back in and kick out to the reading. Okay. Of course, hydrogen electrons would be horrendously removed and they would never leave. But in the case of an acid chloride, you have a chloride ion that can leave. And so, what I've done now is form an aldehyde. Now, of course, aldehydes can be attacked by hydride ions. So, there's nothing to prevent you from having your second hydride ion come in. Attack, form your alkoxide ion, just like we did a second ago. But by now I've added 2 hydride ions. And then, when I put this whole thing in water, then we finally quench. But by this time, I've added 1 and 2 equivalent of hydride ions.
Does the hydride ion have to come from the same reducing agent both times?
It's your reagent here is lithium aluminum hydride. So yeah, basically you're using 2 equivalents of the lithium aluminum. It needs to be a strong hydride reagent like lithium aluminum hydride. Sodium borohydride is not going to do that for you. So this here, attacking an acid chloride or an ester, right? Here you could have like, let's say an ester, that would also be less of a good leading group, but you could still get it to react. But in here, the source of this has to be lithium aluminum hydride. Sodium borohydride is not okay. So that's, we can reduce aldehydes and ketones in a couple of different ways, either with hydrogen, hydrogenation, or with sodium borohydride, or with lithium aluminum hydride. But an acid chloride or ester will only be reduced by lithium aluminum hydride. We don't have an option. Okay. So those are basically your reactions. Add a hydride, from the oxide ion quench from the alcohol. Stronger reducing agents will add two hydrogens, so you're starting from an ester or acid fluoride. Then at the end of the day, we're going to end up adding two hydrogens and forming the alcohol. You really cannot stop at the aldehyde with this reagent. It is possible to come up with a slightly different reagent in which we are going to add very large groups over here and drop the temperature to like -78 degrees. When you do that, it's a much slower selective type of hydride addition, and then it only adds once and you can stop at the aldehyde. But for now, let's not worry about that, we'll get to that eventually. But you can always tweak things to get it to work like you want. But right now, with straight lithium aluminum hydride, if you're starting with an acid, chloride, or ester, you're gonna go straight to the alcohol, you cannot stop. Okay. So that's pretty much it. Your aldehydes and ketones, you can reduce with sodium borohydride or with a stronger lithium aluminum hydride, both of them will work. But your ester, your acid chloride, for those we're going to need the stronger lithium aluminum hydride. Okay. And again, hydrogenation only works, I'm sorry, a hydrogenation you can hydrogenate both a double bond carbon oxygen and a double bond carbon carbon. Hydride ion, which is nucleophilic, requires an electrophilic carbon. Hydride ion only attacks a carbonyl, whereas hydrogenation works on any double bond, be it polar or non-polar. But hydride ion requires a polar double bond, meaning a carbon double bond oxygen. So if I put this molecule and hydrogenate, both this double bond and this double bond are going to be reduced. But if I put sodium borohydride, only this portion is going to be reduced, and the carbon double bond carbon is not going to be touched at all. Okay? So yes, both will have an effect on the carbonyl, but not both are going to have an effect on the carbon compound. So depending on what you want as a product, you choose which reagent to use. All right, so let's work on some of these problems. So first of all, we have this molecule with an aldehyde on this side and an ester on this side. I want to know what is going to be my product first when you're putting sodium borohydride followed by quenching. And second, when you put this same molecule but now with lithium aluminum hydride followed by quenching, show me what the products are. really ought to have these problems in front of you so that you can work without needing to be constantly looking at the screen. But I suggest that you print all the blank problems and definitely before an exam, reprint them again so that you can practice on them and make sure that you can do that without any additional help. Okay, so this is this molecule, right? I'm just drawing it with line angle formula. Sodium borohydride is going to touch the aldehyde, but not touch the ester. So the aldehyde is going to be reduced to this alcohol, but the ester is going to be untouched. You need to keep track of your carbons, right? We have a carbon here, 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 here. Okay. It's important that you recognize the carbon from the carbonyl is the carbon that now has an OH attached to it. And in line angle formulas, I no longer draw these hydrogens on this carbon, but obviously they're there, and I've added an additional hydrogen here, and now I have two hydrogens. Now, lithium aluminum hydride will touch both the aldehyde and the ester. So at the end of the day, this carbon here will also now have an OH, because this is my leaving group that's going to leave. And right now I have these 4 carbons and these 4 carbons, right? And the rest leaves because that's a leaving group.
That's it? What is the best leaf? How does it become a leaving group that leaves?
Yeah, these are a hydrogen and methyl group of horrendous leaving group. Something like a chloride becomes a much better leaving group. Hydroxide ion is meh, but hydride is strong enough that it can push it out. Okay, so I'm trying to make this alcohol by 3 different methods. So I'm asking the same molecule, make it 3 different ways. And the first, I want you can start from any substrate that you want, but I want you to make this alcohol as a product using a nucleophilic substitution reaction, an SN2 reaction. The second way of making this alcohol, I want you to reduce a carbonyl compound. And then the third way to make this alcohol, I want you to use a Grignard reaction. So go ahead and make this alcohol with 3 different ways. What is the substrate in SN2 reactions? Methyl. So I'm going to put an alkyl halide and then come in with which nucleophile? take an L. Hydroxyl, right? OH minus. That's going to be the nucleophile that makes the chlorine and bromine leave and take its place. That's a substitution. Alright, so for the first one, I'm going to, let's say, put chlorine, bromine, some leaving group, and then have this react with hydroxide ion. This hydroxide ion, of course, is coming from some salt, like sodium hydroxide. But basically, this is a nucleophile that will attack this sp3 carbon and have this chlorine leave. And that will then give me that product, right? I'm substituting the chlorine for the OH. Now, reduction. When I reduce a carbonyl compound, I'm effectively adding hydrogen to each of these, and you're reducing to the alcohol. So I need to look at having the carbon and oxygen that are the carbonyl that is going to be reduced, right? So this carbon and this oxygen need to be the carbonyl, which is now going to be reduced to the alcohol. Either an aldehyde or potentially an acid chloride that I will need to reduce twice. Let's leave it at an aldehyde and either soluble hydride or lithium aluminum hydride or hydrogen. Any one of these would reduce the aldehyde to the carboxyl, to the alcohol. In the case of soluble hydride, I need to quench. In the case of adding hydrogen, palladium, I don't need to quench. That's all that I need to do. And that's going to reduce this to the alcohol. Lastly, I need a Grignard. A Grignard is a nucleophilic carbon that attacks a carbonyl to make that carbon-carbon bond and then OH. So we're still going to have the carbonyl here. This is going to be the nucleophilic carbon that attacks this carbon double bond oxygen to make this bond. Alright? So this portion is going to be the Grignard that attacks the aldehyde formaldehyde to make this bond. So we make Grignards from halides. So the halide that I need in here is what else? A bromine, a chlorine, something like that. And then first, I put my magnesium with some ether. I don't usually like the ether, but certainly that's part of that complex that you're forming. Second, I need to add the carbonyl. And in this case, that's one carbon with two hydrogens and an oxygen. Right? That is the carbonyl that I'm going to be using. So this is going to attack, form the hydroxide ion, CH2, and eventually OH. So quench. Right, and make this carbon-carbon bond right here, and this becomes a CH2 OH. So a variety of different ways in which I can make the same point. Now, the last exercise is a little bit more the kind of exercise we're going to be doing now in organic chemistry. Something that involves a multi-step synthesis. Something in which, I tell you, well, I want you to make this. And here you're starting materials. This is what you have to work from. And at the end of the day, you need to know the reactions that are going to get you from here. Now, first and foremost, you need to look at the pieces that you're starting from and figure out where those pieces are in your product. So, clearly here there's a benzene ring that we still have in here. Clearly here there's this cyclopentane that is connected to at least a carbon. And here's a cyclopentane that is connected to at least a carbon. So, without question, somewhere in this synthesis, I'm going to need to make this bond. I'm going to need to somehow connect these two together. Okay? The most difficult thing is going to be making your carbon-carbon bond always. So that's how you need to strategize. Putting and taking out oxygens and things like that, that's relatively easy. But the carbon-carbon bond should be the crux of your synthesis. What reaction is going to make this combined with this? Right now, you know two ways of making a carbon-carbon bond. One was if you had some sort of terminal alkyne, we came in with a strong base from the alkoxide ion, the alkynyl anion, and this was a nucleophile which could then go ahead and attack, let's say, a carbonyl in this case, to give an atom. That's this reaction here, using these two electrons to form a bond between this carbon and this carbon, allows you to make a carbon-carbon bond. Now, a more general approach to this that applies not just to sp carbons but to any carbon is a gradient. I could certainly do a gradient with this, but in this case I'd be starting from some sort of a chloride or bromide or iodide, which can be attached to an sp carbon but can also be attached to an sp2 carbon or an sp3 carbon. This is a lot broader. And you put your magnesium, make the gradient, you add your carbonyl, whatever it happens to be, you quench, and at the end of the day, you form that critical carbon-carbon bond, let's say something like that, whatever it happens to be. So, right now that's the only two ways that you know to make a carbon-carbon bond. So if I'm asking you, how do you make this carbon-carbon bond? The answer is going to be one of those two. Which one? Because this is not an sp carbon, this is not a hydrogen, this is a halide, an aromatic halide. So Grignard is the only way that's going to get you there. Now, once I connect this carbon to this carbon, then I'm gonna need to massage things to end up with this effect. But let's start with that connection. I'm gonna get this homobenzene. First, I add magnesium. Then I'm gonna add the aldehyde, to which the magnesium is, the gradient is going to add. And we're gonna quench this. And after I quench, this piece is now gonna connect to this carbon, which is gonna be, at this point in time, an alcohol here. Right? So this piece is coming from bromobenzene. This piece this piece is clearly coming from this. Okay, now I still need to get here. How do you make epoxides? From what? Well, from what substrate? From an alkene. Remember, if I collect money, I'm rich. If the answer is chapter 8, okay? 90% of the functional groups you can make from an alkene. So you're fairly safe whenever I ask you, where are you making this from? Chances are it's from an alkene. I'm just being facetious, but a lot of things are made from alkenes, and certainly epoxides are made from alkenes. Okay? So, in doing synthesis, there's also what we call retrosynthetic analysis. That is, you look at your product and you say, oh, how do I make this functional group? What do I make it from? Sort of step back one step. Okay, I can make it from this. Okay, and then how do I make this? I can make it from this. And how do I make this? I can make it from this. So, this is my final product. I know that I can make this final product from an alkene. If I have a carbon double bond carbon here, the way that from alkenes you make peroxides is with a peroxy acid. Often you use something called methachloroperoxybenzoic acid and CPDA, but you can use other peroxy acids as long as you do it in a neutral solvent, because if you do this in acidic water, then your process opens into the 1,2-diene. But as long as you keep this in a neutral solvent, and you use a peroxy acid like MCPDA, you're gonna get the epoxide. Okay. So, can I get from here to here?
Yeah.
That's a dehydration reaction, and you want elimination of an alcohol, right? All you need to put is put some acid, right? Heat, and that's going to be basically you're eliminating these two and forming a double bond here. That is your typical E1 elimination. So those are different, you need to do both. You need to look at where you're starting from, where you end. First of all, evaluate which pieces are coming from where. Second, evaluate what are the key carbon-carbon bonds that you're going to form and what's going to be the strategy to form those carbon-carbon bonds. As we move through organic 2, we're going to add 3 or 4 more ways of forming carbon-carbon bonds. That's it. you have a very limited repertoire of reactions to form those carbon-carbon bonds. And gradients should be foremost in your mind. That is so common, such a common way of making carbon-carbon bonds. And then you do your little retrosynthetic analysis. Okay, how do I make epoxies? I can make those from alkenes, that type of thing. But you need to attack it from both ends. What reactions do I need to use to move forward? Retrosynthetic analysis, how do I make these functional groups from one other functional group? And it's kind of a combination of the two. Okay? All right, so we're done with chapter 10, which is basically review from organic 1. Now we're going to start with new material, which is organic 2. So let's go on to chapter 11. So in chapter 11, chapter 10 was how do you make alcohol. Chapter 11 is reactions of alcohol. Right? Remember, chapter 7 was how do you make alkenes. Chapter 8 was reactions of alkenes. Well, 10 is how do you make alcohols, and 11 is reactions of alcohols. We're going to go functional group by functional group. How do you make it? Reactions. Okay. So alcohols and different reactions. Let's start it off. So one, no, stop. We're going to look at oxidizing alcohols, oxidizing them to ketones, aldehydes, carboxylic acids. Then we're going to look at converting an alcohol into a good leaving group. We need to do that so that we can then, using a good leaving group, come in with a nucleophile and have this leave. But this is not going to leave as hydroxide, but it's going to leave as phosphate or as water. So we're going to look at ways of converting an OH into a good leaving group so that we can then do reactions like coming with a hydride ion and form something like that. Okay. Then we're going to look at substituting your OH for something else. We looked at the reverse, substituting, let's say, a chloride by OH. Now we're going to look at the reverse of that. We're going to look at dehydration. We looked at adding water across an alkene to give an alcohol. Now from an alcohol, we're going to dehydrate to an alkene. We of course know those reactions as E1 eliminations. We're going to look at esterifications, add an alcohol to carboxylic acid to form an ester. We're going to look at other reactions from an ethers and things like that. So a bunch of different reactions with alcohols. First, starting with oxidation. We just looked at what is reduction, right? So in general chemistry, you studied the fact that oxidation is the loss of electrons and reduction is the gain of electrons, right? In organic chemistry, we follow atoms more than electrons. But of course, those atoms have electrons. So a reduction is looking at an atom that has electrons and is adding those electrons to something else. So when we were looking at having a carbonyl and coming with a hydride ion, we're adding these electrons to the carbonyl. And so right? First you come in with, say, sodium borohydride, and then you quench, and at the end of the day, you have reduced. You have reduced because you have added hydrogen, but hydrogen with electrons, okay? So my carbonyl has been reduced to the alcohol. This would be a reduction. A reduction because we're adding electrons. Reduction is the gain of electrons. So the carbonyl is gaining electrons from the hydride. So it's a reduction, okay? Now, in this context, this is a reduction of the carbonyl to the alcohol. This is my reducing agent. It is causing the ketone or aldehyde to be reduced to the alcohol. So this right here is my reducing agent. Your reducing agent is going to be oxidized, while your carbonyl, while this is my reducing agent, this that is being reduced is my oxidizing agent. Right? It's always the opposite. Whatever is being reduced is the oxidizing agent. Whatever is being oxidized is the reducing agent. Right? This is always a redox reaction. Something is being reduced because something hasn't been oxidized. And each of them is causing the other partner to be reduced or oxidized. So I can recognize this to be a reduction because I'm adding hydrogen. Or I can recognize this being a reduction because this is a reducing agent. Okay? My reducing agents, we looked at them, are hydrogen with electrons. So either a hydride ion, like sodium borohydride or lithium aluminum hydride, or hydrogen gas, which has 2 electrons between those 2 hydrogens, so it's contributing electrons as well. So, and in here, we can use some catalyst, a little plasma, whatever. Those would be reducing agents, not H plus, because that does not contain electrons. Okay, so these are your reducing agents that cause a reduction. Oxidizing agent that cause oxidations. So oxidation typically means adding oxygen. It also means removing hydrogen with electrons because oxidation and reductions are opposites. So if a reduction means, as far as the substrate, adding hydrogen with electrons, right? Then oxidation means removing hydrogen with electrons, right? But it also means adding oxygen. 1 or 2 oxygens, or a halogen. Halogens kind of behave like oxygens from an electron standpoint, which of course means that a reduction is removing oxygen or halogens. Okay? So, how would I add oxygen? Well, I'm going to have a reagent in which I typically have a metal with a bunch of oxygen. And that's going to be my source of oxygen. My metal is often chromium, but it can be things like manganese and a variety of things. So you're going to see reagents like chromic acid or sodium dichromate or whatever. I mean, bunches of things, or permanganate ion. typically as potassium permanganate. All of these things where you have this metal with a bunch of oxygen are typical oxidizing agents. And therefore, you recognize when you see that oxidizing agent, you say, oh, this is an oxidation. Okay. So, you can, again, oxidation would be loss of hydrogen or the gain of oxygen or halogen. Reduction is the gain of hydrogen with electrons or the loss of oxygen or halogen. What is not an oxidation or a reduction is anything that involves H plus or gaining or losing water or gaining or losing HS, because that's one of each, right? So they cancel each other out. So if you're talking about eliminating water from an alcohol to form an alkene, or adding water to an alkene to form an alcohol, or adding HBr to an alkene to form an alkyl halide, those are neither oxidation nor reduction. Okay. So let's look at problem 1 here. So for each of these reactions, I want you to tell me whether I have an oxidation, a reduction, or neither. Do you see an oxidizing agent? Where do you see an oxidizing agent? Right here, right? Chromium with a bunch of oxygen. We don't need to look at this much further. This is an oxidation. Now, of course, what we're doing here is we're removing hydrogen and putting a double bond here, okay? But ultimately, you know this is an oxidation because you have an oxidizing agent. So, alcohols, primary alcohols, are oxidized to an aldehyde first, and at the end to a carboxylic acid. So let's say that you started with methanol, okay? You're gonna remove hydrogens and put a double bond here. Removing hydrogen is an oxidation. So now we're gonna make an aldehyde, okay? Now I'm gonna add an oxygen here. So in this case, this is an oxidation because I'm removing hydrogen. In this case, this is an oxidation because I'm adding oxygen. And that would be a carboxylic acid. But I need to start from a primary alcohol to form a carboxylic acid. Because if I start from a secondary alcohol, right, so if I had a secondary alcohol, when I remove hydrogen and form a double bond here, what am I forming?
Ketone.
Ketone, right? So secondary alcohols are oxidized to ketones. course, the reverse is true. So carboxylic acids are reduced to aldehydes, and aldehydes are reduced to primary alcohols, and ketones are reduced to secondary alcohols. Okay?
And then tertiary alcohols can't be oxidized, right?
Correct. I need at least one hydrogen to be removed. So if I had a tertiary alcohol, I cannot reduce that because there is no hydrogen here to reduce. So this cannot be oxidized. Okay? So, we're working on problem. So, this we removed hydrogen from the secondary alcohol to form the ketone. This is an oxidation. And we very quickly could recognize this from the oxidizing agent. Do you see a reducing agent here? Whenever you're adding hydrogen either in the form of H2 or hydride ion, that is a reducing agent, which obviously means that this is a reduction. Now the others. In here, I'm simply replacing OH with bromine. I am not adding hydrogen. I am, in essence, removing an oxygen and a hydrogen, so it's one of each. But effectively, I'm not changing the oxidation state. This is not an oxidizing or reducing agent. This is neither an oxidation nor a reduction. What type of reaction is this? Dehydration. Adding or removing water is neither an oxidation nor a reduction. Right? Adding water or removing water is neither. In this case, we're removing water. But the reverse will also not be an oxidation or a reduction. Okay? And adding or removing HBr is neither a reduction nor an oxidation. So this is also neither reduction nor oxidation. Okay? But having some idea about those oxidizing and reducing agents, and we'll see some more that are not so obvious, but these are very, very common. So those you should have a good grasp, recognize immediately. This is an oxidizing agent, of course this is an oxidation. All right, so what we just went over, right? If you're starting from an alkane and you add oxygen to make an alcohol, that would be an oxidation. And then you oxidize your primary alcohol to an aldehyde, and you oxidize your primary to a carboxylic acid. Your aldehyde to a carboxylic acid. Or if you're starting from an alkane like this, oxidize to an alcohol, secondary alcohol, further oxidation will give you a ketone. Of course, from a tertiary alkane, I could oxidize to a tertiary alcohol, but this cannot be oxidized any further. Yes.
So primary alcohol will always end in a carboxylic acid in oxidation?
Well, it depends on the strength of your oxidizing agent. So if you're using a milder oxidizing agent, and that is typically something called pyridinium chlorochromate, or PCC. It is still a chromate ion putting a bunch of oxygen, but the pyridinium thingy makes it less active. And so you can stop at the aldehyde and stop there. But any of the others, sodium dichromate, chromic acid, potassium permanganate, yes, will get you directly to the carboxylic acid. Okay. Of course, in the case of the ketone, it doesn't matter what the heck you're using because you cannot oxidize this any further, so you can use mild or strong, you're still going to stop. All right, so secondary alcohols, any kind of oxidizing agent is going to get you to the ketone. And if you want to stop at the aldehyde starting from a primary alcohol and not continue, then you're going to use this particular reagent called PCC, pyridinium chlorochromate, and we always use PCC, we don't want that thing. There's an additional reagent that you can use, but it's a reagent that you need to make in situ with a bunch of different reagents, whereas PCC is a nice powdered orange powder that you just add in. 99.9% of the time we use PCC. So we're not going to worry about a swan oxidation. We're just going to use PCC as the mild reagent that gives us aldehydes. Okay. Tertiary alcohols don't oxidize. So here's your summary. What are the products? What are the reagents that you will be using for these oxidations? So let's look at problems 2 and 3. So what alcohols and what reagents would you use to form the product A, which is a ketone, or the product B, which is an aldehyde? Go ahead and draw the starting material and draw the reagent that you would use to form the ketone. Basically looking at adding hydrogen here, that is the starting material. Right? This secondary alcohol and adding hydrogen here, and this primary alcohol, these would be your starting materials. Right? Now, to form an aldehyde, which is the one reagent that I told you, to stop at the aldehyde and not over-oxidize to the carboxylic acid. Whereas in here, there's a variety of reagents that I can use, like sodium dichromate, typically this is some sulfuric acid, something like that. But I could use PCC in here as well, right? Pretty much any reagent will oxidize a secondary alcohol to the ketone. Okay? A lot of what we're going to do is this thinking backwards. Here's the product. How do we make this product? So we need to get used to the thinking backwards, the retrosympathetic analysis. Okay? Okay, we're going to leave this here. We're going to start on problem 3 next time. Make sure that you finish with all the homework from chapter 1. If you want to be all caught up, you should be done with all that homework, including the one at the end of the chapter. And maybe just get started reviewing off of those spreadsheets.